Let's look at some data as we begin to describe our final intermolecular force. So we have some data that is temperature versus molecular weight here. And we would expect that this temperature, by the way, is the boiling point. So water's boiling point is at 100 degrees Celsius. That's expected. Okay, so we would expect that as the molecular weight and the number of electrons increases, the boiling point would also increase because of an atom being more polarizable, right? So for these four, starting with carbon, silicon, germanium, tin, all these hydrogen compounds, that trend holds, right? We get an increase in boiling point. But oxygen is smaller than sulfur, and so we would expect it to be the lowest boiling point down here to follow the trend. But look, it's way up here. It's extremely high. So the question we got to try to figure out is, why is that? What is it that's holding those water molecules together so tightly to increase the boiling point so much? What's happening is something known as hydrogen bonding. The dipole-dipole interactions experienced when hydrogen is bonded to nitrogen, oxygen, and fluorine are much, much, much stronger than a traditional dipole. And we call these interactions hydrogen bonds. So in this case, we have a nitrogen bonded to a hydrogen and an oxygen bonded to a hydrogen. We get a hydrogen bond here. This interaction between the really negative end of this water molecule and the really positive end of this NH3 molecule. The same thing happens with two water molecules or with another NH3 and H2O. Okay, so these dashed lines are our intermolecular forces known as hydrogen bonds. Hydrogen bonding in part comes from the very, very high electronegativity and small radius of nitrogen, oxygen, and fluorine. When hydrogen is bonded to one of those, and there's examples here of oxygen and fluorine, the hydrogen nucleus is really exposed to where it's not ionic, but that negative is really concentrated on the oxygen or the fluorine or the nitrogen. Okay, so this is really, really, really positive, and this is really, really, really negative without being a completely plus or minus charge. So we get a really strong electrostatic attraction bond here holding those molecules together. As I've said before, if you're watching on the PDF or you have access to the PDF, you can click this link to watch an animation about hydrogen bonding. Water is one example of a substance that is less dense in the solid state than in the liquid state. Makes the behavior of water really special. So solid water or ice floats on liquid water. If it didn't, life on Earth would be very different. For instance, lakes would freeze from the bottom and fish couldn't survive the winter. Hydrogen bonding explains this. It creates the space in the ice that has the molecules spread out, making them less dense than the liquid water. And again, if you're watching from a PDF or have access to it, you could click on here to watch the animation of the water-ice transition, which just demonstrates those water molecules spreading apart to be less densely packed in ice than they are in liquid water.